Okay, welcome everyone to this continuation of Lie theory. Lie theory, more representation theory. Oh, more representation theory. And there will be even more representation theory to come. I'm very happy, as you can tell. Hopefully you're very happy as well. Maybe not. I can't blame you at all. But we'll have a look. It's actually pretty natural, and hopefully you will like it eventually. It's linear algebra, right? Linear algebra. Who doesn't like linear algebra? Okay, so essentially the picture I have in mind is, well, we have our Lie group and we have our Lie algebra, and the Lie group acts somehow globally on some object and the Lie algebra acts locally on some object, because one of them is a derivative of the other and one of them is the integral of the other, if you want. Yeah? So linear motion, a group acting as infinitesimal operators, is then so a group acting on something, and then you take infinitesimal operators, so differential operators or something, and then you get an action of the Lie algebra. Yeah? The Lie algebra wraps a different. What a difficult name. Who came up with this name? It's a derivative of a Lie group representation in a very controlled sense. Yeah? So it's kind of the local symmetry, the local global. So there are three ways that I always like to repeat. There are probably more, but there are three ways that I always like to repeat to explain what a Lie group and a Lie algebra is. The Lie group is a global object, the Lie algebra is a local object. Yeah, the Lie group is a smooth object, the Lie algebra is its derivative. So derivative integral, if you want. Global, local. And then there's also the x block picture. One of them is the logarithm of one and the other one is the exponential of the other. Anyway, so in this case, like the local, right? It's the derivative at the point. So kind of the local picture, and of course you would expect the local picture to be a bit easier. And the surprising magic that happens, the usual Lie group, Lie algebra magic, is that the local picture does not lose all that much information. You would expect, oh, this loses so much information. But no, it surprisingly doesn't. There are some subtleties, obviously, but surprisingly a lot of information is already in the local picture. And then you just study a representation of Lie algebras because it's a bit easier than representations of Lie groups, right? Okay, so here essentially what I have in mind. So a vector, a Lie group element is already a vector. A Lie group is already a vector space. Is assigned to a linear map as before, and the bracket is represented as before. So essentially the bracket is now translated into matrices. Literally, into literal matrices. And how I think about this is the following. So usually a Lie algebra representation is kind of a local representation. So here is a Lie algebra element of SO2. So SO2, the capital SO2, the group SO2 is just rotations of two space. And you should think of the Lie algebra one as tiny, this is not tiny, but anyway, tiny rotations of an epsilon rotation, right? So you have a V and you send it to something like that in an explicit formula. That's what Lie group representations, Lie algebra representations usually are, like infinitesimal symmetries, continuous symmetries. So in this case, an infinitesimal rotation. That's just what it is, an infinitesimal little rotation with some epsilon somewhere. And abstractly, it's almost the same as before. You just have a matrix now for every Lie algebra element, and they represent respect the bracket. Well, that's just literally what it is. And the usual idea, hopefully at this point clear, but I'm happy to repeat it again, is that you have a smooth thing, and you take the derivative, and you get the Lie algebra thing. You have a group thing, you take the derivative, you get the Lie algebra thing. Right? So we actually need to start with a smooth representation here, not just with an arbitrary representation of our little Lie group. And then you can literally take the derivative, and then, as before, the curves become first order linear operators, which are your Lie algebra representations. And then you can exponentiate and take logarithms and go from one to the other. Take the integral, you can take the derivative. Local versus global. The usual story. No surprise here. But I want to give you some examples. And then we do some very explicit example in a second. Okay, so matrix actions. GLN acts on x to the n by matrix multiplication. It's kind of still the same example. And that's usually called the defining representations. Yeah? So SON is infinitesimal rotations, like that picture for two-dimensional space, are a bit more difficult to draw in 500-dimensional space, but the same type of idea. And SL2 is like a really nice toy model for the whole story, and essentially the SL2 representations work as follows. They organize themselves in a two-variable Pascal's triangle picture. So I have two variables x and y, and I have 0 degree, I have first degree, I have second degree, third degree, fourth degree, fifth degree, whatever, sixth degree, right? So whatever, let's say here, third degree, you have x cubed, x squared, y, x, y squared, and y cubed. And SL2 acts on this thing, we can actually do that. The Lie algebra SL2 is the following thing. So SL2, oh, can I do that? SL2, here we go, has three, so traceless 2x2 matrices, has three interesting operators. There's this one, traceless, there's that one, and there's a diagonal one, which I'm going to ignore for a second. There's a diagonal one. And this guy, let's do it here. So this guy here acts on these representation by, in this way, so it takes the derivative with respect to x and it multiplies by y. So this is a differential operator, right? It takes a derivative with respect to x and it multiplies by y, so it goes from here to twice here. This does the opposite. It takes the multiplies by x and takes the derivative with respect to y, so it goes from here to here, for example, or from here to here. So the picture upstairs would look like that. So our little matrix, one matrix does this and one matrix does that. So this matrix goes to the left and this matrix, this matrix goes to the right. And our final, so differential operators, right? It's a local action. It's very nice. So this is like very easy differential operators on the polynomial space. And this guy does something like x dx plus y dx, or y dy. So it keeps where it is, right? So here in my picture here, if you take x dx, if you derive it first by x and then multiply by x, you're still here. And if you take the derivative first by y and then multiply by y, you're still here. So this final matrix is an eigenoperator with on this space with eigenspaces, those guys. So that's a standard example of a Lie group action, which we will see in more details later if this was too fast. And the only thing you need to remember from this action is that all of this are differential operators, very easy ones, right, on a polynomial space. But this is how you can think of Lie algebra representations. Lie algebra representations are something given by differential operators. And SL2 will be such a beautiful toy model for everything. Why SL2, you might wonder now? Well, 2x2 matrices is the first interesting case. 1x1 matrices are just not that exciting, honestly. So 2x2, the first interesting case, you already get some funny differential operators coming up. Okay, cool. So the big picture, sorry that was too much detail, but eventually you have to do it. I'm so sorry. Oh, life is not fair. Life is not designed to be fair, that's for sure. Yeah. So usually Lie algebras are linear spaces and their representations are often easier than Lie groups. We can talk about the subtlety in a second. Let's just zoom into this picture. This is literally how I think about it. So usually you have an abstract representation and an incarnation. The incarnation is a representation. Yeah? Abstract number 3, incarnation, whatever, 3 triangles, 3 apples, 3 minutes left before I need to go or something like that. Finite groups are usually finite symmetries, like symmetries of this little guy here, the tetrahedron. Yeah? So that's usually finite symmetries or some permutation diagrams. Lie groups or Lie algebras are, so here's a nice thing. Lie algebras are like the vector space version of it, but Lie groups literally are continuous symmetries, like rotations of a space or some other things. And SL2 is just our favorite example. As a Lie group, it's determinant 1 matrices. As a Lie algebra, it's traceless matrices. And then as a Lie algebra, it's literally just a linear version of that. That's literally it. That's a big picture, and we're going to study Lie algebra and Lie group representations. Now. Well, maybe not now. You're still free to go starting next time. So starting now. There's one little subtlety. So the Lie algebra has more representations. The Lie algebra is an easy object, has more symmetries. So not every infinitesimal story automatically integrates back to the group. But I would call that a minor issue. You can basically ignore it. Essentially, Lie algebra wraps is still a local symmetry, even without a global group action in general, right? So that's what you would expect, I guess. And I call it a subtlety because it's really not that bad. Yeah, if you know an action around this point, there's no good reason why you should have a general action of everything globally, right? And it happens, just what it is. But most of the time, it's still pretty good. So everyone likes Lie algebra representations. And we are going to start with some terminology next time. And eventually, we do so many examples. It will be so good. And eventually, you don't even need to remember what a Lie group is anymore. Anyway, I hope you enjoyed this video, and I also hope to see you next time.